I want you to picture something for me. Close your eyes if you have to. Well, unless you're driving, obviously.
Yeah, please keep your eyes on the road.
Right, safety first.
Yeah.
But if you can, visualize an oil painting, very classical, done in that grand, dramatic propaganda style of the 19th century. Dramatic lighting, serious posture. In the center, there's a figure, but it's not a human general. It's a cat.
Okay, a cat.
And not just any cat. This cat is dressed in a full military uniform. Epaulets, the high collar, the sash, looking very stoic. In fact, it is dressed exactly like Emperor Napoleon.
Wait, does it have the hat, the big bicorn hat?
It absolutely has the hat. And just to dial up the absurdity level to 11, this Napoleon cat is holding a piece of cheese in its paw.
That is a very vivid image. I can see it.
Right. Now, here is the question for you. If you showed that image to a standard computer vision system from just a few years ago, what would it actually say? It would probably span the pixels and just say, cat, maybe costume.
If it was really good, it might say cheese.
Right. But would it get the joke?
No, definitely not.
Would it understand the history, the reference, the sheer absurdity of a feline French emperor holding a piece of dairy?
Likely not. It would see the objects, but it would completely miss the meaning. It misses the cultural context and the humor.
Exactly. But today, we're doing a deep dive into a system from our source material that actually does get the meaning. We are looking at Flamingo. And before anyone asks, no, we are not talking about the pink bird standing on one leg in Florida.
Although, interestingly enough, the bird does feature pretty prominently in their testing data.
Fair point. But we are really talking about a visual language model, a VLM, developed by the team at DeepMind. This isn't just a computer that sees or a computer that reads. It's a model designed to bridge that gap entirely.
And that bridge is really what makes this specific paper so significant. For years, AI has been somewhat segregated. We've had models that are incredible at analyzing images, telling you that's a stop sign.
Yeah.
And we've had models that are incredible at processing text, like writing essays or code.
But they lived in separate houses.
Exactly. And Flamingo isn't just mashing them together. It's an architectural innovation that allows a model to reason across both simultaneously.
It's the difference between looking at a picture and describing it versus looking at a picture and actually talking about it.
Precisely. It allows for a conversation that flows naturally between visual inputs, like images or videos, and text.
And the headline feature here, the thing that honestly feels a bit like sci-fi to me, is something they call few-shot learning.
Right. That is the core breakthrough we need to talk about.
The idea that you don't need to show the computer 100,000 pictures of a cat to get it to recognize a specific situation. You show it a handful, maybe just 2 or 3 examples, and it figures it out. It learns on the fly.
Which is incredibly close to how humans learn. If I show you a gadget you've never seen before, say a strangely shaped kitchen tool, and I explain it once, you understand it.
Yeah, I don't need to see a million spatulas to know what it does.
Exactly. You don't need a massive data set to grasp the concept. Flamingo is trying to replicate that immediate adaptability.
So our mission for this deep dive is to unpack how Flamingo actually works. We're going to look under the hood at the frozen brains inside it, the special bridge they built to connect them, and the massive amount of specific web data required to teach it to think like this.
It is a fascinating case study in efficiency and architecture.
Let's start with the problem, though, because before Flamingo, AI seemed to be operating in these strict silos. Why was it so hard to just get a text model to look at a picture?
It really comes down to how these different models interpret the world. Traditionally, you have these distinct pillars. On one side, you have vision encoders. These are great at taking a grid of pixels, an image, and turning it into mathematical features. They can spot a dog, a car, a tree.
Okay, so they are the eyes of the operation.
Correct. On the other side, you have large language models, or LLMs. These have read the entire internet. They can write poetry, summarize emails, predict the next word in a sentence, but they are effectively blind. They process tokens, which is text, not pixels.
So for a long time, if you wanted a system that could look at a picture of a dog and write a poem about it, you couldn't just introduce them and hope for the best. You had to perform a very expensive process called fine-tuning.
Right, and expensive is the key word there. Fine-tuning means you take your models and you train them again, specifically on thousands and thousands of examples of, say, images of dogs paired with poems about dogs.
That sounds exhausting.
It is. You have to wire them together and update all their weights, their internal neural settings, so they get good at that one specific task.
It sounds incredibly rigid, too. Like if I trained it to be a dog poet, and then I showed it a video of a golfer and asked for a critique of their swing, What happens?
It would fail completely. To get it to understand golf, you'd have to start all over again. You'd need a new data set of thousands of golf videos with commentary, and you'd have to fine-tune it again.
So it's super resource intensive, and it just creates these narrow experts that can't generalize.
Exactly. And that's where Flamingo flips the script. It moves from fine-tuning to what they call interleaved processing.
Right, because Flamingo is designed to handle a stream of information that is mixed up. It doesn't just want an image and a label. It wants a conversation. It can take text, then an image, then more text, then maybe a video, and output freeform text at the end.
Yes.
The example from the paper that really landed this for me was the teddy bears on the moon scenario. It sounds ridiculous, but it demonstrates the reasoning perfectly.
Oh, it's a classic demonstration of reasoning versus just labeling.
So they feed the model a generated image. It shows two teddy bears. They're on the lunar surface on the moon, and they're sitting in front of what looks like an old 1980s computer.
A very bizarre scene.
Right. And the user asks the model, what are they doing? Flamingo replies, they're having a conversation.
Yeah.
Then the user asks, what object are they using? Flamingo says, it looks like a computer.
Now, so far, that is standard object recognition. A basic vision model from 5 years ago could probably tell you teddy bear and computer.
But then the user asks, is this surprising?
And this is the key moment.
Flamingo replies, yes, it is surprising. And the user asks why. And Flamingo says, I think it is surprising because teddy bears are not usually found on the moon.
That is a massive leap. Think about what is actually happening there. That is world knowledge. The model has to know what a teddy bear is, what the moon is, understand the relationship between them in the real world, that bears don't go to space, and apply all that to this fictional image to determine that it is unusual.
It's reasoning, not just pattern matching.
Exactly. It's common sense, which is historically very hard for computers to grasp.
So let's get into the how. How do you build a brain that can do that without retraining it for every single scenario? When I looked at the architecture diagram and the source material, I saw a lot of snowflakes.
Ah, yes. The snowflakes represent frozen models, and this is a very clever engineering choice. The team at DeepMind realized they already had two very powerful tools. They had a vision encoder, specifically a model called NFNet F6, which is excellent at seeing.
Okay.
And they had a massive language model called Chinchilla, which has 70 billion parameters.
Chinchilla. Cute name, incredibly massive brain. But the snowflake icon means frozen. That implies they can't learn right.
It implies their weights are locked. DeepMind didn't let Chinchilla or the vision encoder update their original structure during the Flamingo training.
But why? If you want them to work together, wouldn't you want them to change and adapt to each other?
If you change them too much, you risk something called catastrophic forgetting.
That sounds ominous, like a total system wipe.
It's a serious problem in machine learning. Imagine you have a brilliant professor who has read every book in the library. That's your language model. Now, you want to teach this professor to describe paintings. If you force them to focus only on paintings for months, if you fine-tune their brain too aggressively...
They might start forgetting the books they read.
Exactly. They lose their general knowledge, they become a great art critic, but they forget history, science, and how to write a good sentence.
Okay, so by keeping them frozen, DeepMind preserves all that pre-existing intelligence. The professor stays smart.
The professor stays smart, and the eyes stay sharp.
But if the vision part and the language part are both frozen, how do they talk to each other? You need some kind of translator in the middle.
That is exactly where the bridge comes in. They inserted new trainable layers between the frozen layers of the language model.
This is the secret sauce.
It really is. It consists of two main innovations. The first is called the perceiver resampler.
Which honestly sounds like a piece of equipment from Star Trek. Captain, the perceiver resampler is offline.
It does have a ring to it,
Okay.
but it solves a very practical computational problem. A high-resolution image, or worse, a long video, contains a massive amount of data. It's very heavy. A language model, on the other hand, likes neat, orderly inputs, tokens.
Right.
If you dumped raw visual data directly into the language model, it would just choke. It's too much noise, not enough signal.
So the perceiver resampler acts like a funnel.
Precisely. It takes that variable, massive amount of visual information, whether it's a small picture or a long video with thousands of frames, and it squashes it down into a fixed number of visual tokens, specifically 64 tokens.
Wait, only 64?
Yes, 64.
That seems tiny. I mean, you're taking a whole video of a golf swing and summarizing it in 64 little packets of information.
It is extremely aggressive compression. But it works. It forces the model to extract only the most essential visual features needed to understand the scene. It strips away the background noise and keeps the semantic meaning. It essentially says, here are the 64 most important things about this visual scene.
Okay, so the perceiver resampler packages the visuals into these 64 tokens. Then what? How do those tokens actually get into the brain of the language model?
That's the second innovation, gated cross-attention dense layers.
That is a mouthful.
It is, but the mechanism is actually quite elegant. They use a technique called tan gating. And here's a really cool part. When they start training this bridge, the gate is initialized at 0.
Meaning it's closed.
Meaning the language model completely ignores the images. At the very beginning of training, Flamingo acts exactly like a normal text generator. It doesn't see anything, but as training progresses, the gate slowly opens. The model gradually learns to let the visual information influence the text generation.
That's a really cool analogy. It's like the model starts out blind, just talking to itself based on what it knows from books, and then slowly opens its eyes to the world around it without getting overwhelmed.
That's a great way to put it. And because of this slow integration, the language model never gets confused or broken. It just gets enhanced. The text brain remains intact, but now it has visual context.
So we've got the frozen brains, and we've got the bridge. Now we need to talk about what this actually enables, which is this few-shot learning concept.
Or in-context learning, yes. This is where the user experience completely changes. Instead of programming the computer, you are essentially prompting it.
Let's walk through the arithmetic example from the paper, because this blew my mind. They didn't show the computer digital numbers. They showed it photos of handwritten notes on lined paper.
Right. So the prompt provided to the model looks like this. First, an image of a handwritten note saying 2 plus 1, and the text output 3. Then an image of a note saying 5 plus 6, and the text output 11. That is the context. That is the few-shot training.
Just giving it a couple of examples, and then they showed a new image. 3 times 6.
And the model outputs 18.
That is wild to me. Did you just read the numbers? It recognized the pattern. Like, oh, we're doing math based on these scribbles. And it applied the multiplication logic.
And it did it from just 2 examples. That is the power of the heavy pre-training combined with this architecture. It is identifying the task dynamically. It doesn't need to be retrained to do math. It just needs to be reminded that math is the current topic.
There was another one involving animals that showed off that external knowledge really well, the geography example.
Yes. The prompt shows a picture of a chinchilla and says, this is a chinchilla. They are mainly found in Chile. Then a picture of a Shiba Inu and says, this is a Shiba. They are very popular in Japan.
And then they showed a flamingo.
And the model completes the pattern. It writes, this is a flamingo. They are found in the Caribbean and South America.
Think about the layers there. It recognized the bird. It understood the pattern of the prompt was identify animal plus identify location. Then it accessed its internal encyclopedia, the language model, to find where flamingos actually live and wrote the sentence.
Exactly. And when they ran this against benchmarks, standard tests for AI, the results were staggering. On 16 different benchmarks, Flamingo set a new state-of-the-art on 6 of them using just few-shot learning.
And when you say few-shot, usually that means about 32 examples.
Yes, often around 32. Compare that to the previous state-of-the-art models, which were fine-tuned on tens of thousands, sometimes hundreds of thousands of examples.
So Flamingo is using orders of magnitude less data for the specific task and still winning. It's vastly more efficient.
Yes, but there is a catch. To get a machine to understand this image-text pattern, you can't just train it on random stuff. The data diet really matters. You can't just feed it dictionaries.
Right, the data diet is absolutely critical. And this is where the paper highlights a specific data set they built called M3W, or MultiModal MassiveWeb.
Which sounds like a wrestling federation, but it's actually a brilliant data set. They scraped 43 million web pages. But the innovation wasn't just the sheer volume, it was the structure.
Because usually when people train these visual models, they strip out the images and just keep the text. Or they create simple pairs of image plus caption, clean data.
Exactly. But DeepMind kept the web page structure intact. Text, then an image, then more text, then another image. They treated the web page as a continuous sequence.
Why does that matter so much?
Because that is the exact pattern of few-shot prompting. Here is some text. Here's an example image. Here's the result. By reading millions of web pages formatted like that, the model learned a concept of interleaved communication naturally.
It learned that images and text flow together to tell a story.
It did. And they actually tested how important this was. They did an ablation study, which is where you remove one piece of the system to see if it breaks. When they removed the M3W dataset, performance dropped by over 17%.
That is a massive collapse in machine learning terms.
It really is. It proves that just showing a model, a picture, and a caption isn't enough. It needs to see the flow of information to learn how to learn.
They also threw in video data too, right? 27 million short videos.
Yes, the VTP dataset. This was crucial for temporal understanding. There's a great example in the paper of a man playing golf. The video shows him swinging the club and hitting the ball. The model is asked what happens next.
And it predicts. He falls down.
Which implies it saw the swing, analyzed the balance of the golfer, and predicted the future motion. It's not just describing a static frame, it understands action over time.
That is incredibly impressive. But I have to ask, is it perfect? I mean, we're talking about a model that uses a large language model as its brain. We know those things can have issues.
Oh, it's not perfect, no. And Flamingo definitely inherits the weaknesses of its parents. Because it uses chinchilla, it can still confidently state things that are simply not true. We call these hallucinations.
Right, we just make stuff up.
Exactly. It might look at a blurry picture and confidently tell you there's a specific bird there when there isn't, just because the text pattern suggests there should be a bird. It's a creative writer, and sometimes creative writers hallucinate.
And what about simpler things? Like, can it tell me what kind of flower I'm looking at?
Surprisingly, for pure classification, like just looking at a flower and saying rose or tulip, it actually lags behind models like CLAP.
Really?
Yeah, CLAP is a model purely designed for contrastive matching, just matching an image directly to a label. Flamingo is better at the conversation, the open-ended discussion, but it's actually a bit less precise at the simple labeling game.
It's a philosopher, not a cataloger.
In a way, yes. But its versatility is its strength. There's an example of visual question answering, or VQA, in the sources. They show it an image of an apple. But taped to the apple is a piece of paper with the word iPod written on it.
Like a prank. Someone labeled an apple as an iPod.
Exactly. They ask the model, what does the sticker say? It answers iPod. Then they ask, is it printed or handwritten? And Flamingo answers, handwritten.
That's nuanced. It's distinguishing the text from the object and analyzing the font style.
It creates a lot of utility. It shows that the model isn't just seeing an apple, it's reading the entire scene.
We should probably touch on the societal impact here too, right? Because the source material explicitly warns about some of the risks.
It does, and it's a very important point. Because this model relies heavily on a pre-trained language model, it can reproduce gender and racial biases, or output toxic language that was present in its original training data.
And there's also the issue of the barrier to entry being lowered.
Right. Because you don't need a huge specific data set to train it to do a new task. It's much easier to adapt. That's great for researchers, but it also increases the potential for malicious use. It makes it easier for bad actors to generate harmful, context-aware content quickly.
It's a double-edged sword, for sure.
Yeah.
So let's zoom out a bit. What does this all mean for the listener? We've got frozen brains, bridges, teddy bears on the moon. Why should they care about Flamingo specifically?
I think the key takeaway from the paper is the shift in how we interact with AI. We are moving away from the era of fine-tuning, where we act like engineers turning screws to fix a machine for one specific job. We are entering the era of prompting generalist models.
It's less about coding and more about communicating.
Yes. The perceiver resampler and that interleaved training data created a system where you can explain a visual task to a computer almost as easily as you'd explain it to a human. You show, you tell, and it understands.
It really does feel like we're crossing a threshold.
I think we are. The paper suggests that as these models get bigger, and DeepMind went up to 80 billion parameters, they get disproportionately better at this few-shot learning. They are becoming better students.
Which leads to a provocative thought to wrap things up. If a model like Flamingo can learn to understand a complex visual scene, like Teddy Bear's reasoning on the moon, from just 4 examples, does the future of AI look less like training a computer and more like teaching a student? Are we becoming less like programmers and more like teachers?
It's a profound shift. We are moving from defining rules to providing examples. We are showing the machine what we want, rather than strictly programming how to get there.
Something for you to chew on. Next time you look at a photo, ask yourself, how would I explain this to a machine? And with Flamingo, you might just have to show it another photo to get the point across. Thanks for taking this deep dive with us.
Our pleasure as always.
See you next time.